convergence of linearized kinetic equation, turbulence. And we are, as a reminder for everyone, get the word out that we are starting at 9:45 because several of us teach at 11, and we will need some time to set up the recording and the Zoom for our classes. So it's kind of important we finish slightly before 11. So thanks again, and Erwan, I'll give you the floor.
Okay, thank you very much, Jalal. Happy New Year to everybody.
Happy New Year to you. Oh, I'll mute. Can we all mute, please? Except
I am muted.
And
is it okay? Do you hear me?
yes, we can hear you. You are unmuted. Everyone else should be muted.
Okay. So what I would like to present is something that that started quite a long time ago, with the idea of trying to justify, at least in some case, some kinetic dynamics in wave turbulence. So so here I will present you some essentially some. I will first start with the discrete nonlinear Schrodinger equation. I will explain you why, and then the results that I will state will be in fact for a quadratic model, essentially a Petyaashvili model, like in the book of Nazarenko. Well, I will explain in more details, but let us start with the discrete nonlinear equation, Schrodinger equation. So why discrete? So discrete is just that the equation that we consider is set on a grid. So so the unknown here, the phi, are functions defined on a grid, and belongs to some discrete grid embedded in R2 and of size n, or 2n. So it's a square of n by n, 2n by 2n plus 1 by 2n plus 1 points. And you replace the standard Laplace operator that you have in the Schrodinger equation by a discrete one. The discrete one, so it's just here. So I will try, oh yes. So this is the discrete Laplace operator. So you can recognize in A1 here, you have a second derivative, discrete second derivative in the direction 1, and in A2 a second derivative in the direction 2. So why this model? So why this model? Because in fact, if you consider the exact Schrodinger equation, then you will have some unbounded spectrum. Well, in this case, it is well known that if you can take the Fourier transform of the phi a and obtain an equation that is a spectral equation set on a domain that is here essentially minus pi pi. This is a domain, the spectral domain. So, and it is bounded, and for me it will be extremely important. So I will ask two questions, well, several questions, but the very first setting is to analyze the continuous limit in frequency, which means that n goes to infinity. Because when n is finite, this is a huge system of ODE, right? So you can apply Cauchy-Lipschitz and you have existence. But when n goes to infinity, you have an infinite dimensional discrete system. And this system has a continuous spectrum, and you can expect some scattering, some dispersion, etc. So it's a dispersive PDE when n goes to infinity. The second parameter here, epsilon, is the size of the nonlinearity, and it is supposed to be small. Then I will consider random initial data. So I will not be studying, for example, solitons for this equation, which is a very interesting case of study, but statistics of solutions. And I will add at some point some random forcing and random dissipation and dissipation. So if you take the Fourier coefficients of these points, then you end up with an equation that is this one, which is an equation on the Fourier coefficients of these systems, which has a part that oscillates here. I, this is a complex imaginary number. I u dot equals omega j uj, and the omega j are exactly these frequencies made of sinus. Actually, I taught this 1 month ago, 2 months ago. So the frequency of the discrete Laplace operator are the sinus square of j, essentially. And the nonlinearity here, which is local in A here, becomes a convolution in Fourier. And this will be my models. So a system, a huge prey-predator system with a linear part and a small, in some sense, nonlinear part that has interaction through a convolution. If you want to obtain NLS, if you want to obtain results for NLS, essentially you have to divide the discrete Laplace by h square. Then it is more or less like having a mesh that goes to 0 of size h, and then the omega j becomes these numbers here. And when h goes to 0, you can see that at least formally you go to j square plus j1 square plus j2 square, the eigenvalue of the Laplace operator. But I don't want to introduce the, so if you want to deal with the nonlinear Schrodinger equation, would amount to, would be essentially introducing this new other parameter and have a new parameter that goes to 0. But I don't want to talk about this one. Okay, so so now about the random initial condition. So in wave turbulence, so my goal is to follow, in fact, the proof or the derivation of the standard derivation of the wave turbulence, of the kinetic equation in wave turbulence. I want to follow the proof and try to prove some convergence result. So if you look at the random initial conditions considered in wave turbulence, they are made they have these random phase assumptions, which says that the Fourier coefficients are decorrelated mode by mode. So the expectation of UK and UK bar, so these are complex numbers, either k equals L, and this is something, but when k is different from L, this is 0. And the prediction consists in finding some equation for the variance, the expectation of UK square. And it is predicted that this nk are well approximated by the solution of a kinetic equation, which is this one here in the case of NLS. So it is the main, there are 2 points, but the first one is that it is a real equation. There is no I. The second point is that there is an epsilon square. Recall that epsilon here, if you look at the equation here, epsilon is essentially the size of the nonlinearity. So epsilon square means that in some sense you go to the next step in some asymptotics. And this equation has a sign, which means that because it's a real equation, it is a kinetic equation, and you have an H theorem and a possible relaxation towards some stationary states, etc. So it's an irreversible equation. And the first equation was Hamiltonian, the NLS equation, the discrete NLS, and this one is not Hamiltonian, it is a kinetic equation. And this equation has stationary solutions, so 1 over omega k, 1, and this one, 1 over modulus of k. And they are stationary solution, essentially because this equation is now set on a resonant manifold. Okay, so these are the standard prediction of wave turbulence. And so I will recall now the main arguments that you can find in the physics literature. So the main argument follow this path. First, you conjugate by the free flow, which is standard. So you start to write down your variation of constant formula or Duhamel formula. You end up with this system, which is a system where you have no linear part, but some oscillating terms in the nonlinearity, depending on differences between the linear frequencies. Then you calculate the evolution of the Vj square. This is exact for the moment. And then you integrate by part when it is possible. And essentially, it's always possible. Why not? Generically, this delta is non-zero. At some point, you take a continuous limit. So here you change the sum to an integral. At some point, you neglect some terms, O of epsilon squared, square. And then you develop, so you reintroduce in this term the value of this guy. This is O of epsilon, but this is a boundary term in t and in 0. So it's a local term in time. And now when you take the derivative of this term, you end up with now 6 nonlinear interactions. You have 6 modes that interact. And then you make some assumption, or so you claim that it is true, that you have some random phase and Gaussian assumption, saying that when you take the expectation of this term, in fact, either you have one k that is equal to 1m, and then it gives you vk to the square, and also L equals to J and also R equals to N, and so you have exactly this, and the other term are 0. You assume that you have propagation of the random phase assumption for all time. And then you end up exactly with a closed, not exactly, you end up with a closed equation on the nk, but you have this small denominator here. And this closed equation is this one. You have something that is, well, it is more or less like this one. You end up with something that is, well, you have coefficients, combinatorial coefficients. You have to divide by these small denominator coefficients, and you multiply by the n. But here there is like a Hilbert transform. There is, if you divide by 1 over something, you have a problem. So you have a problem, meaning that you have to define correctly the object. And to define correctly the object, you have several ways. You can take the Hilbert transform, which will give you something real. Here you will have the principal value. And if you have the principal value here, then this term is real. So if you take the Hilbert transform, you will have a real term here. So imaginary part, you have nothing. So to obtain something imaginary, you have to add some dissipation and define this singular integral by adding some dissipation, and takes the dissipation going to 0 to use this kind of formula. And then you will obtain we will obtain something which has here an imaginary part, I, and this will give you the value here of this huge integral, but concentrated on the resonant manifold delta omega equals to 0. So second invocation, or second hope, you can do this. Knowing that to do this, you know that we have some discrete number of mode. You want to add dissipation, but you want this dissipation to be able to exactly correct, to write this kind of formula in a discrete way. So this is the second difficulty. Okay, so so the argument, one of the main argument, of course, is the main argument is based on the fact that if you start with a random phase assumption on the initial data, the main argument says that this is still true for a time of order 1 over epsilon squared, which is the time scale of the kinetic equation. So first, this has to be proved. So, but now, what can we expect? If we do not have any dissipation, and if we do not consider this, okay, we forget for statistical solutions for the moment, we just look at this. If we do not have dissipation, if we first let n goes to infinity, it means that we have discrete NLS on an infinite lattice. And then, well, maybe not in the 2D cubic case. There are many specialists of this probably, but at least if the dimension is higher, this is true. You get scattering. Scattering means that essentially you behave like the free flow. And if you behave like the free flow, it means that the solution is essentially this one, an oscillation here, oscillations in Fourier, and this preserves the random phase assumption, because this is, if the solution here is just, the initial value here is just exponential of e theta, where theta is a random variable independent in J, then this will be preserved. So a scattering result will give you a random phase, the propagation of the random phase assumption. The other scaling is that when epsilon goes to 0 first, then you see the grid, you see the geometry of the grid. It means, and then n infinity. So if you start first, epsilon goes to 0. If you look at here, when you do this kind of, when you divide here by 1 over delta omega, then it will depend on the Diophantine condition that you have on omega. And you see that, for example, just in this case, the omega, they are this sinus 4 divided by h square, sinus square of sj, j1, etc. So you can imagine plenty of situations for the Diophantine conditions on this omega j. Imagine, for example, that you take a grid where you have not exactly the same mesh in the 1 and 2 direction. You have an irrational ratio between the two. Imagine that the numerical grid is not made of rectangles but of trapezoid. Then you will have omega j that have some behavior, but generically they are not resonant. But the way they are resonant depend. I mean, on the other hand, if you do a spectral method, for example, for NLS, you have here exactly the J1 square plus J2 square, you will have resonances. So in the second situation here, in the second situation, epsilon goes to 0 first, then n goes to infinity. Essentially, you fall into some normal form results, and you will have conjugation to an integrable flow for generic system. And so also in this case, you will have some random phase assumption propagated. But in these two situations, you have no kinetic description. And if you add some dissipation, the problem is that this dissipation has to be bigger than the continuous limit if you want to reproduce the delta concentration. Because if you want to discretize, in fact, here this formula in yellow, so you take a discrete integral, then the delta has to be much larger than the mesh of the integral. So delta has to be much larger than 1 over n. So it cannot be a completely small dissipation. This dissipation has to be greater than 1 over n if you want to do this concentration. Okay, so as I said, so it should be general if you, because as I said, for example, NLS, you can approximate by many different finite different schemes. You will have other omega k, other Diophantine condition. Now, in many experiments, so here I'm talking under the supervision of my physicist colleagues. In an experimental setting, usually you have forcing. Forcing by, let's say, in some modes, you impose some for example, some periodic forcing in time. But it's a bit hard to work with periodic forcing. Also, if you add an infinite number of sinus kt, then it is essentially the same as forcing by white noise. So the idea is to model, in fact, the forcing in a first step by stochastic white noise. Let me also give you another problem in this another mathematical problem coming. And it is due to the very singular nature of this random phase assumption. If I look at here this nonlinearity, so J, this is what you get. So this is indexed. The index is fixed. What is the size of the nonlinearity? So you know that you have n square mode because you have a huge square. You have n square mode. So a convolution here, if you just count the number of terms that are here, you have, for example, n squared choice for k, n squared choice for L, and then m is dictated by j. So you have n to the 4 terms. But if you invoke some random phase assumption, then in fact, this term is much, much smaller because you must have k is equal to m or L is equal to m. So in fact, this is only O of n squared. So if you want to see a kinetic equation on a time scale 1, you have to divide not by 1 over n to the 4, but only by n to the 2. So here, the size here of this term is epsilon n squared. So if you essentially, if you want to have deterministically this term small, you need epsilon much, much smaller than 1 over n. And so you will fall into the normal form and arithmetic problems. Okay, so from the deterministic point of view, you have this problem, this singularity problem of perturbation, singularity perturb problem, and from the statistic point of view, to have something that is here of order 1, you need to have the RPA assumption. So you need to show that it is propagated. So just for this term, you can, I mean, I here put questions. I don't know, but there might be some statistical scattering result saying that if you start with a Gaussian measure for this term, and if you first let n to infinity, can you make a meaning of this statistical scattering, and the same for normal form. And for the second question, I will give you some answers. But without forcing or dissipative term, you see that at least in the two main regime, so first n to infinity where you have scattering, first epsilon to 0 where you have normal form, I see no reason why you would expect a kinetic equation. Of course, I put a question mark. It's not a claim. But probably you can prove that you have statistical scattering and generic statistical normal form in these two regimes where when you have no forcing or no dissipative term. Okay. So now the main idea of this work is to say, okay, so based on these remarks, I have to add some noise. And if I have to add some noise or some forcing, probably the easiest way from the mathematical point of view is to force constantly the angles by a Wiener process. So to consider a stochastic wave equation. So it's just exactly the same as before, except that I have added this term, which is what you think. It is what you think in the sense that if you look, so V is just a Wiener process. Circle is a Stratonovich product. This is just to say that the solution of this guy is what you think is this term, exponential of I lambda lambda Wn. So the exponential of the Wiener process. So and lambda is a new parameter. So it's again a small parameter, which is essentially the size of the noise. So the big advantage of this is that it is a dissipation that acts only in the angles. So you do not destruct you preserve the L2 norm of this term. So you preserve all the Sobolev-like norm that you can imagine if you do not add the nonlinearity. And so it's an equation that is hypoelliptic, and so you have the noise only in the angles, and it's a model, in fact, to say that you will constantly force in the angles by a stochastic noise. And here, in the present work, I will force all the modes, which is, of course, not what you will do in practice. In practice, you will only force in some spectral band, and not for all the modes, I guess. Okay, so let me just give you what is the interest to do this from the mathematical point of view. So let us consider just the linear operator acting mode by mode. So it is completely diagonal here. You see, if you remove the nonlinearity, this term is purely diagonal. It acts only on uj, and it does not. So let us look at this term. If you look at this term, in fact, it is what we call a Hamiltonian stochastic system. So it's a general way of defining. So these are stochastic system preserving the Hamiltonian structure. So it was, I think, first introduced by Milstein, Repin, and Tretiakov in 2002. So here, if you just take the real and imaginary part of U, then you end up with a system that has here, it's not very beautiful, that has some Hamiltonian part and another Hamiltonian part, but with a different time scale, which is stochastic. And it turns out that if you take the Stratonovich product, it is done exactly to say that H is an energy that is preserved by this flow. So it's a stochastic system, but with an invariant, which is given by the Hamiltonian system. And what we did with the Tony Lelièvre, in fact, was it was for doing molecular dynamics to sample some microcanonical measure. So you have a stochastic system evolving on a hypersurface, and you want to be stochastic, ergodic, but inside the hypersurface. So okay, this is the system. Just a slide to recall the Ito formula, because so here it is a general stochastic ordinary differential equation. So you have a deterministic part and a noise here. So n is the index and alpha, d, capital D is the size of the noise. Then the Ito formula, this is the only thing to know for this analysis, in fact. It says that if you take phi, which is a function, and if you look at the evolution of this function here, so phi in 0, against the process here, yt, and if you calculate the expectation of this starting in x is deterministic, so you take a point, you sample many trajectory, and you take the expectation, and this expectation satisfies the Kolmogorov equation, which is above. It's a linear equation, and L is the classical transport transport operator associated with the ordinary differential equation. And you have a second order part coming from the noise. And it is given by this formula. So of course, the interest here is that here you have a transport operator that you regularize in some sense by a second order operator. And so when you do singular perturbation, you're happy to have a second order operator. So in the case of random phase, what do we have? So if I take this this equation here, then I apply the Ito formula, and then you will see that the corresponding operator here is in fact P dq minus Q dp, which is a rotation operator. So if you look at the Ito formula in this case, if you look at the Kolmogorov equation, you will obtain dt phi. If you take the expectation of some observable depending on P and Q. So typically, if you look at modulus of U squared, this will be expectation of P squared plus Q squared. Then it satisfies dt phi omega times the rotation operator and lambda square divided by 2, the same rotation operator square. And so if you write down in action angle, so you are in a polar coordinate, then the transport operator is just the rotation of theta of an angle omega, and the effect of the noise is to regularize this transport operator by a Laplace operator in theta of size lambda square. So you see the interest of the noise from the point of view of statistical analysis is that here you have an operator, and okay, it is not exactly invertible, because if you Fourierize here the theta, you will have omega scalar k. Omega scalar k depends, the inversibility depends on the Diophantine property of omega. But for this one, no. It is always invertible. So if you now look at the same equation, but from the point of view of the density, so if you draw initial data with respect to a density in action angles variables, then it is well known that you can define the transport of the density, rho of t, by this dual formula. So if you take the expectation of an observable along the flow A of theta, so the stochastic flow, then you can define the flow of the original observable according to a moving density, and this moving density evolves according to the adjoint of the Kolmogorov equation, which is here the same because the Laplace is self-adjoint, and minus this one because the delta is a skew adjoint. Okay. So now, what is a random phase? Assumption for the initial density. It is just saying that the initial density does not depend on theta. If this does not depend on theta, so the angles essentially they are when you have several modes, and if you have angles that are not exactly the same, I mean, you will have here some oscillating factor, and it will go to 0. So if you look at the evolution of this equation here, then you can prove that the density is solution in Fourier. If you take Fourier, is a solution given by this. So if you have lambda equals to 0, if you have no noise, then you just have oscillations. The density oscillates. But when you have lambda positive, strictly positive, then this goes to something that depends only on A. Because when K is non-zero, the term goes to 0. And so essentially, this random phase forcing will encode, in fact, the random phase assumption. So now we can see that this is now the final model. So lambda is changed to square root of 2 delta for obvious reason, but delta, no, because delta now will be the scale, the time scale of the term, which means that if you forget about the nonlinearity, if you look just at the first equation, at the linear equation, if you start with any distribution, in fact, then you will have the preservation of the actions, and the correlation between UK and UL will go exponentially to 0 with respect to a time scale 1 over delta. That's why I put here square root of 2 delta. Okay. So it will force the random phase hypothesis. Okay, so this is the same system, but written as a Hamiltonian system. It's just taking UK equals PK plus QK. So the linear part is diagonal. So of course, well, no, I will not comment on this now. And if you look in action angles variables, so you just take polar coordinates for the Fourier coefficients, then the system becomes dA equals epsilon times something, the nonlinearity, d theta, the angles, omega n, of course, and the solution is just IT omega n, and the Wiener process. So if you look at this, it is essentially a Langevin system. It's a Langevin system. You have a Hamiltonian system and a noise here in the impulse. In fact, you do not need here. You do not need to add dissipation because theta is bounded. So you just have to put the noise here, and theta being in a torus, it will be essentially a huge Langevin system. And you know that Langevin systems are often can be hypoelliptic, which means that you tend towards some a possibly unique invariant measure of the system. So it's okay. So now, okay. So now so when you have such a stochastic system, you look at the invariant measure and random initial data. So I will draw the initial data with respect to some probability density function rho n, which is just smooth. Essentially, it will be a Gaussian or slight modification of a Gaussian. So, okay, this is just a definition of a PDF, and the probability to have this one in a domain ON is just the integral of the density. And the evolution of the density is done through the Fokker-Planck equation, written now for this huge system. And for this huge system, it is exactly the same as we had before, but on a torus, on a very large torus. And you see that the standard omega c dot, the transport operator omega c dot delta derivation with respect to theta is regularized by a huge Laplace operator, delta theta. So this is the evolution of the density. So of course, if you do not have the noise, you do not have this dissipative part. So it's a dissipation, but only in the angles. And you see that delta is small, but delta is linear. So in fact, delta, little delta, delta theta is a regularization of the transport operator, which has some singularities when you have resonances. So it's a way to encode the quasi-resonance that will appear when you will divide by something. Okay. So now invariant measures. So imagine that. So let us look at measures that are Gaussian measures in PQ, real and imaginary part of UK, that are under this form. Zn is just a normalizing factor. And if Mn, this is this guy. If it is an invariant of the deterministic system, then in fact, it is an invariant of the stochastic system. Why? Because it depends only on p square plus qk square, which are the actions, and they are invariant by rotation. So the noise will not destruct the invariance of this measure. And this is fundamental, for me at least, to obtain a priori estimates. If I do not have this, I'm not able to do anything for the moment. So what does it mean? It means that if I draw some random variables, some initial data with respect to this measure, I will have the expectation of any function of this will be constant. For example, if I calculate the expectation of uk u bar L with respect to this measure, which depends only on p square, so on the moduli of uk square, then I will have the random phase assumption, and the expectation of uk square is equal to gamma k, and gamma k, I said if it is an invariant of the deterministic system, it corresponds to what we call Rayleigh-Jeans waves, which means standard invariant of the systems. So for NLS, think of the L2 norm. And for wave equation, I will give you the more details, okay? So the strategy now is to take NLS, take the L2 invariant, you have a bounded domain, you can define it without any problem. It will be a finite quantity, and you start with fluctuations. So these fluctuations around the invariant measure, so it's a notion that I think was first, so this maybe Isabelle can say more about that, but at least it is in the paper of Bodino, Gallagher, and Saint-Raymond concerning the L2 approach of the hard-sphere dynamics. So I will consider fluctuations of this invariant measure. And if you do fluctuations, then, well, you end up with a linearized kinetic equation. Linearized kinetic equation around the solution gamma k, which corresponds to the stationary solution of the Boltzmann of the kinetic wave equation. And for the nonlinear dynamics, so Di Viola showed before Christmas talk where they said that they have some result concerning the nonlinear dynamics. I think in a setting very close to this one. So I'm very happy to see the developments. So, but okay, now NLS, if you look carefully into the technical details, you have some unpleasant features. You have some singularity in the resonant manifolds. You have some first term that is not exactly zero, etc., etc. So, in fact, I first consider quadratic models. Typically, think of real ways models, so KDV, Benjamin Ono, KP, Boussinesq systems, that are 2D with a quadratic nonlinearity, which means that you have a cubic Hamiltonian. And typically, the domain of frequency is parameterized by kx, ky, where kx is strictly positive. This is really, I mean, if you worked a bit with KDV or Benjamin Ono, this is typically the kind of equation you will have. And to make some calculations, I took the frequency of the Kadom-Tseff-Petchashvili equation, which are given exactly by this one, and eta is a parameter that will be useful. Okay, like a Diophantine parameter. And the natural invariant I was talking about, so this would be the L2 for the KP equation, for example, gives you in the Hamiltonian formulation a solution of the kinetic equation that is exactly this one, 1 over kx. So it's a one-directional cascade, if you want. If you want to realize or simulate such exactly this system, you take a pseudospectral discretization of the KP equation, and then you start with something that is equidistributed everywhere, and then you see what happens. FPU would also be a very nice system, but I don't remember. There are also some unpleasant things in FPU. Okay, so the wave turbulence predictions for this quadratic model is that, well, in some asymptotic range of parameters, the expectation of the UK square are well approximated by a solution of a kinetic equation, which is here. So, okay, I do not enter into the details of the combinatoric of these coefficients, so it's plus or minus, etc. But it's a kinetic equation. They are real. The equation is set on a resonant manifold. Here you have only 3-wave interaction and not 4 waves like in the NLS, so it's slightly simpler. D sigma is the microcanonical measure on the resonant manifold. So the measure induced by the ambient space. And this equation has gamma k as a stationary solution. Okay. So the result that I obtain is the following. If you draw initial data, so not exactly as according to the invariant distribution, but such that the expectation of the UK 0 are perturbations of the gamma k with G0 smooth on the domain. So the domain, of course, avoid the singularities kx equals 0, etc. So you want to have the less technical problem possible. Then you can identify the limit, the following limit. So you take expectation of UK t divided by epsilon square. So the time is 1 over epsilon square. You remove the gamma k part. You renormalize by n to define what I will call fluctuation. And this is a number. And now if you take epsilon or n goes to infinity, whatever you can make epsilon first or n first, to 0 and infinity, and then the noise goes to 0, then you end up with f of t, and f of t of k is a solution of the linearized kinetic equation in gamma j. So you see, this is just, I replace here this one by gamma and let R here, this one by and after the other one by gamma, and I obtain a linearized kinetic equation. Okay, so this is the main result. So of course, several comments have to be made. The scaling. So if you look at the scaling, if you look at the scaling here, you see there is a 1 over n. So of course, when n goes to infinity, it goes to 0. So so it means that we make some fluctuations. But what does it mean? And if you look carefully at the Feldman-Hachek theorem, 2 Gaussian measures in infinite dimension, either they are completely, they do not see each other, or they are equivalent. So you have a density with the one with respect to the other. So this n is here because it is, to my knowledge, the only way to have estimates that are independent on n. So the kinetic equation is hidden in some asymptotic expansion of in 1 over n. In 1 over n. Okay. There is here the word weakly, and it is very weak. It is weak in the sense that you have to use some coarse graining procedure to obtain a limit. So I will not enter into the details, of course, today. And the limit do not commute, in the sense that if you have no noise, and if you take epsilon to 0 first, then generically, which means that for almost all eta, this is the parameter, I recall, the parameter in the frequency. If you remember, the frequency are these ones. So eta is a free parameter. It is like if you imagine that you have a Diophantine torus. You set Kp on a large Diophantine torus, for example, or something like that. Then for almost all eta, in fact, you have no kinetic description in this regime. So delta, so no noise, epsilon to 0 first, and then n to infinity, then nothing happens, generically in eta. And but in fact, if you change the delta and you make it go to 0 last, so first epsilon to 0, then n to infinity, and then delta to 0, you will obtain the kinetic equation. So at least there is a regime where you can prove that the noise is completely crucible. So there is another regime, so delta 0, but n to infinity first, and epsilon to 0. And if you look, this is more or less the regime studied by Lukarinen and Spohn, but not exactly for the same in the same initial data. So they draw the initial data with respect to a Gibbs invariant measure. So the expectation of UK are constant, but you can find the linearized equation in some space-time covariance, which in some sense is the expansion of the scattering operator. So it's a bit different. But again, you find the linearized equation in some expansion. This is more or less the same thing. Okay, so I will just, I'm not sure if I'll have that many time because you want to finish at 45.
You still have 10 minutes roughly, so that's okay.
Okay, so I will just comment at least on the fact that it is not an empty theorem, which means that we have some distribution that satisfies the hypothesis. And in fact, and also a technical point that I find interesting. So so what I say is that I can find some rho n, so some initial distribution satisfying the two conditions. So the condition of the theorem. So I have a slight modification of the variance and some bound. And this is exactly the kind of estimates that you have in Bodino, Gallagher, Saint-Rémy. You are close to mu n with respect to this L2 norm. And so typical, so you can calculate that. So you take the initial distribution and you make a slight modification of the variance at each point here of size 1 over n minus 1, and you will satisfy the hypothesis. So these are Gaussians. You just slightly modify the variance. Of course, if G is 0, this is an invariant measure. So you slightly modify the variance and you obtain such an initial data. So this is what you think. You take equirepartition, but you draw with respect to a variance that slightly move. And then you find the kinetic equation for the evolution of the variance. This is it. And the main point, I mean, it seems yes, okay, but in fact, it's really crucial. You have for this norm is decreasing, so you have a uniform a priori bound, and this it's just a calculation that you can follow on this slide. You calculate what does this difference mean. So just here you expand, but look, this one is 1 because integral of mu n is 1. Mu n disappear, but integral of rho n, it is a probability density, it's 1. So you end up with this term. And if you calculate the derivation of this term, because mu n is invariant, then the evolution of this quantity here is just made according to the diffusion. So it is negative. So it goes to so it is a decreasing quantity because mu n is negative. So you have an a priori bound, and like in Bodino, Gallagher, Saint-Rémy, when you have such a bound, you have for free the propagation of chaos and Gaussian hypothesis, etc. And this is an example. If you calculate, you take two modes, Vg square, Vk square, you just expand. And in fact, and in this regime, the gamma j, gamma k is O of 1. The second one, so the fluctuations here is O of 1 over n, and the nonlinear interactions, they are O of 1 over n squared. This one will vanish because it is an invariant measure. This one will give you the dynamics. This one will be negligible. That's why you obtain a linearized equation. Okay. And apart from that, yes, I will also give you just the argument for the deterministic case. You just make the usual procedure. You write Duhamel, you integrate by part, or you do normal form, whatever you like. And the crucial point here is that for any eta, for almost all eta, the small denominators are non-resonant, which means that you will always be able to control the difference of frequency, like this one, by something where you will lose powers of n. And also for the quadratic case, unless you have some the usual resonance, which means that the first one is equal to the second one and the other one. So the term depending on the actions. So you will have non-resonant vectors. So if epsilon goes to 0 first, then you will obtain a standard Birkhoff reduction. And then you also have to make some, so you have to count a bit the number of resonant points on the resonant manifold. It's technical, but this is really that if you discretize a function on a grid, and if you take if you take a generic grid, then you will obtain non-resonant terms. And this is essentially what it means. Okay, and maybe this is I have 2 slides. This is just to say maybe the Ito formula. So the strategy of proof for the stochastic case is to write down the hierarchy of momenta, and the Ito formula makes that you will have this term appear. If you write down usually for standard systems, you will not have this term. And if you look at the interaction representation here, you will have this term coming, and what you will have to integrate by part now is this exponential term. So you see that you will be able to integrate by part when you have here a non-zero when this coefficient R, M, K, L is non-zero, which means that when you are not depending only on the actions, you will integrate by part. You will do your concentration on the resonant manifold, but you will let survive the terms where you have that depend only on the actions. So it's a combination of dissipation in angles and linearization and propagation of KO, because we look at fluctuations. These are the 2 main ingredients. Okay, and this is my last slide. So, okay, so the proof follows the original argument. Apart from that, nothing new. The proof just follows the original argument, but in a weaker sense, because we have to work on the hierarchy of momenta, etc. So if we have no noise, at least in this situation, we have a Birkhoff reduction in some situation, and in the other situation, n to infinity first, we expect scattering. If we want to go to a more realistic setting, I think we have to take the same noise, but only on the spectral band and not in all the angles. But the system will be less hypoelliptic. So it's there must be some. If you remember Mattingly for Navier-Stokes, they prove that if you force one mode, then you are completely ergodic. But it's a proof. So it would be the same sort of argument here, which would more fit to the real experiments. And as I said, it's for me now, I see the kinetic equation as a sort of weak hypoelliptic effect. You force in the angles, and because of the nonlinearity, you obtain kinetic dynamic equations. And I will stop here just to mention that, yes, this story of Braut of Prigogine process, but I will not talk about that. Okay, thank you very much.
Thank you, everyone. Thanks. It was a great talk. We have time for a quick question. If anybody would like to ask, you can unmute yourself. Is everyone okay? Okay. So in this case, I would thank Erwan and remind everyone that next week talk is starting. Oh, yeah, just thank you on chat to Erwan again. So sorry, I thought it was a message. So anyway, next week talk starts at 9:45 because of teaching schedule. So we know we'll have to rush now. Sorry about this, and we'll see you all next week. Thank you very much. Bye, everyone.
Thank you. Thank
Bye.
you.
Thank you.